Well, good afternoon, everyone. Welcome to WARF Innovation Day at SummerFest Tech. I'm Janan Yasri-Mo. I'm with the Wisconsin Alumni Research Foundation, WARF, and we are absolutely delighted to bring this event to you today from beautiful downtown Milwaukee, Wisconsin, where the city is celebrating entrepreneurs and innovators and investors through SummerFest Tech. We're with a live audience here today in Milwaukee. We are also welcoming guests from around the world via a live stream. So we welcome all of you today. I'd like to extend special thanks to our sponsors, Michael Best Strategies and Venture Best, for their support and hospitality. They are sharing their offices with us today for this event. We also want to recognize SummerFest Tech and its support of the burgeoning tech ecosystem here in Milwaukee, Wisconsin, and really throughout the Midwest. Through their efforts of collaboration with regional entities like WARF, we're highlighting Wisconsin in ways that puts eyes on innovations developed in our state. WARF has a near century-long history of advancing university technologies to the market. It's something we're very proud of. This program is organized by WARF Accelerator, which provides campus inventors with business-related support and targeted funding to advance commercially promising technologies closer to the market. WARF Accelerator invests in commercially relevant milestones, proofs of concept, market studies, prototypes, with the goal to validate market potential, demonstrate commercial value, and de-risk technology to attract industry partners and investors. Today, we have 6 pitch presentations that we'll be sharing with you, representing some of the most promising technologies in our state. 4 of them are from the University of Wisconsin-Madison, 1 from UW-Milwaukee, and another from UW-Platteville. First, you'll hear each pitch presentation, and then following the group of presentations, you'll have a chance to ask questions of each of the presenters. Those questions will come at the very end during a panel presentation. As you may have noted, we've got note cards throughout the room, including on your seats. We encourage you to jot down any questions that you have as the program is going along, so it will be easy for you to ask those questions a little later in our program. And that applies to you too, our virtual audience. Please be jotting down the questions that you have of presenters as we go along. Please also consider, if you'd like, to plant those questions in the chat section. We'll be monitoring those, and we'll be happy to bring those up for you at the very end, during the end of our panel presentation. So without further ado, I am going to introduce my colleague, Leslie Mark, WARF Accelerator Associate, who will introduce our first pitch presenter. Leslie.
Thanks so much, Janan. Hi, everyone. So our first pitch this afternoon comes from Dr. Mike Arnold, the carbon expert of UW-Madison. Let's hear more from Mike about his exciting work in developing transformational materials for future technology applications.
Thanks, Leslie. Let's see here. So I'm Mike Arnold, a professor at the University of Wisconsin, and my team has developed a method for aligning carbon nanotubes to create high-performance semiconductors that outperform silicon. This allows for electronics that use less electricity, extend battery life, enable faster computing speeds, and meet the aggressive needs of next-generation electronic devices. So semiconductors are a $425 billion market and really have enabled all of modern electronics. Semiconductors are special materials that could be switched between electrically conductive state. For example, we know that copper wire is electrically conductive, and electrically insulating states, like glass is an insulator. And the switching can happen dynamically, billions of times a second, and that's how a computer works. So semiconductors are the basis of chips and microprocessors in all your gadgets, in your cars, appliances, laptops, phones, and so forth. However, the majority of these devices rely on silicon, which is a materials technology more than 50 years old. And silicon is now being pushed to its limit. It can no longer meet the demands of next generation electronic devices. So we have a new approach to outperform silicon and to potentially usher in a revolution in microelectronics by harnessing carbon nanotubes. So carbon nanotubes are thin sheets of carbon atoms, just one atom thick, rolled into a seamless tube. So this nanotube here, in real life, is about 1/10000000th of a meter in diameter. So these very tiny wires act like semiconducting channels that rapidly conduct electrons. Electricity can be more electricity could pass per area through a nanotube than in silicon. And you can also rapidly switch nanotubes between this on conducting state and this off insulating state with less voltage, which means you use less power. These combination of attributes make them ideal for high speed, low energy electronics, which is exactly what we need. So nanotubes, even though we know they're better than silicon, there's been no commercially viable way for using them in an industrial process that's been developed yet. And the reason is that in their raw form, nanotubes look like what's in the upper left here, this tangled, disordered mess that just does not conduct electricity well. To use nanotubes, we need them like what's shown in the lower left. We need a single layer of nanotubes, very tightly spaced, and importantly, all aligned so that they conduct electricity directionally along their long axis. So creating this bottom left cartoon in real life has been the challenge that has really inhibited the adoption of nanotubes by industry. So we've developed a commercially viable process for overcoming these challenges and orienting nanotubes. And we have a three-step process. So first we take commercial powders of nanotubes, which contain impurities. We extract the desirable semiconducting nanotubes from those powders using what's called the polymer wrapper. We then create a concentrated ink of these nanotubes, which is shown here in purple. And then we deposit these inks in the form of aligned arrays on substrates using one of two methods. The first method that we developed is to rapidly flow the ink over the substrate. A second method is to pull a substrate out through a thin layer of this ink that's suspended on another solvent that's immiscible, such as water. This is all done using inexpensive, very simple solvent-based methods. So our process leverages phenomena of chemistry, self-assembly, and fluid flow dynamics for the rapid and low-cost assembly of nanotubes with unparalleled control over their order. We accomplish this using mild process conditions, and we can ultimately create wafers and electronic components that can be directly integrated into chips and devices using equipment already in semiconductor fabs. So our work will impact the semiconductor electronics market in a number of areas. One is in RF electronics. So this is high-speed electronics in your cell phone, for example, that communicates between your phone and the cell tower. The logic chips are the brains of all your devices. And nanotubes even have potential in future emerging applications like semiconductor biosensors or transparent, flexible, or even stretchable devices that just aren't possible with incumbent materials. So we've already used our methods to create aligned nanotubes uniformly on silicon and quartz wafers on the 4-inch, 10-centimeter scale. And we've created field effect transistors, which are the most basic element of a computer chip that have outperformed silicon in terms of electrical current density. Ultimately, devices 10 times faster that use the same power consumption, or devices that have the same speed but that use 1/10 the power will be viable. So this tech has been developed by a world-class team of experts we've registered over 20 patents collectively and over 200 publications. So I'm a professor of materials science and engineering, and I'm an expert in nanotube and electronics device research. My close collaborator, Professor Pat Gopalan, is also in the materials science and engineering department at UW-Madison, and she's a polymer chemist and a nanotube expert as well. We're working closely with an industry advisor, Jeff Moore, who has founded and exited several advanced materials university spinouts. And Sean Foradori, who's here, is a PhD student in my lab who has over 20 years of industrial manufacturing and management experience in the chemical, food, and automotive sectors. So this tech has been developed over 8 years of research supported by the National Science Foundation and WARF. It's protected by 7 patents and is beginning to catch the eyes of major industry players. So this nanotube alignment process that we've invented promises to enable an order of magnitude leap in an industry where progress has stagnated due to the limitations of incumbent materials. We want to take this technology to market and are looking for an experienced entrepreneur to help start a company. And we are looking for introductions to directors in R&D positions, new product development divisions, in companies in the semiconductor, RF display, and biosensor spaces. Thank you.
Great, thanks so much, Mike. Next up, we have Dr. Randy Ashton, who is the Associate Director of UW-Madison's Stem Cell and Regenerative Medicine Center, which is a founder and a leader in biomedical science. Now let's hear more from Randy about the brain and spinal cord models and their use in predicting neurodevelopmental disorders.
All right. Well, good afternoon. I am co-founder and CEO of NeuroZeta, and it is my pleasure to talk to you about our Rosetta Ray platform, which we believe will transform risk assessment and drug discovery for neurodevelopmental disorders. So why should you care about this technology? Well, there is a fundamental limitation with how we assess the risks for chemicals and their ability to disrupt human development, and that is that we cannot test on human embryos. This is particularly an issue when we talk about development of the central nervous system, the brain and the spinal cord. And that is because no animal models out there have the same complexity of brain and spinal cord development as the human embryo. And so what does this mean practically? Practically, this means that there are thousands of agricultural and industrial chemicals that are released into the market with essentially no data on how they affect human brain and spinal cord development. This causes increased risk of these chemicals, even ones that are EPA approved for being pulled off the market after they've been released, and overall it increases the cost of chemical development. This also increases the rate of neurodevelopmental disorders in our society, as we've seen, for example, with autism, where rates of autism have steadily increased over the last 30 years. Another practical application or result of this is that pharmaceutical companies, they have no viable or cost-effective methods in order to test whether these drugs have a risk for disrupting human nervous system development. Overall, this increases the risk of candidate drug failures, as well as FDA-approved drugs being restricted once they've been placed on the market, and it increases significantly the cost of drug development. We also have no method for investigating how your genetics versus mine actually predispose us to neurodevelopmental disorder risk when exposed to these various chemicals and drugs. And this limits us from developing precision medicine approaches to prevent these disorders, as well as increases the burden of neurological disease broadly in society. So why is this important? Well, we know that during the early stages of human brain and spinal cord development, very early in pregnancy, exposures to various chemicals and drugs, as well as genetic mutations, can lead to severe birth defects, as well as childhood and even late onset neurological disorders. Perturbations during normal human development can increase a person's risk for these particular birth defects, and that is an ongoing systemic issue. These perturbations can be caused by not only your genetic background as well as mutations that you have, but can also be caused by exposures to various chemicals, drugs, and pollutants. And overall, these can lead to things like spina bifida, autism, as well as Huntington's disease. Now, the problem is that we don't know how the combination of anybody's one genetic background combined with their chemical exposures can lead to these developmental disorders, and that's largely because we don't have an accessible model to actually screen and test for these things. And this becomes even more of a risk for companies that are developing these chemical compounds as well as drug compounds, because basically they have to rely on rodent data, which is not equivalent to humans, in order to make these safety risk assessments. And this forces them to make a multi-million-dollar wager when they are taking a chemical drug from product development into the clinic. And ultimately, NeuroZeta hopes that our Rosetta Ray platform will help to mitigate this risk and significantly reduce their costs. The Rosetta Ray solution is essentially a high-throughput platform for modeling human brain and spinal cord development in a dish. And it enables scalable and cost-effective screening of various chemical compounds and their risk of causing a human neurodevelopmental disorder, as well as the ability to probe genetic backgrounds for their own risk for developing these neurodevelopmental disorders. We also can create this platform from patient cells in order to model neurological disorders and use that for novel drug discovery applications. So overall, we can help to increase the predictive capabilities of neurodevelopmental toxicity testing. We can drastically reduce the risk associated with compound development and release, and thereby the cost of those development pipelines. And we can enable novel neurodevelopmental disease models that allow us to create new precision drug discoveries in order to prevent these neurological issues. The Rosetta Array technology essentially bioengineers slices of the developing human brain and spinal cord and puts them into a well-plate dish where we have arrayed tissues that are recapitulating this developmental phenomena and share the same rosette structure as well as cell composition of various regions of the human brain and spinal cord. We combine stem cell engineering, material science, and computer science in order to create a platform where you can seed cells directly into our culture plates, grow those tissues in the presence of various compounds or drugs, and then observe how they affect the formation of these tissues. We can capture these tissues via confocal imaging, run them through our automated or AI-inspired algorithms in order to detect various parameters of these the tissue formation process that allows us not just to tell whether a compound is toxic, but actually gain insight into the signaling pathways that have been perturbed in order to cause that increased risk. Our Rosetta Array platform can be directly applied to developmental neurotoxicity testing and compound discovery pipelines. We can also generate these from gene-edited and patient cells so we can make models of personalized diseases and use those models in order to conduct precision medicine drug discovery. Overall, we're expected to disrupt the $4.6 billion market for animal and tissue organoid modeling. And we have a large opportunity in this space as more bioengineered tissue platforms like ours come out for other tissues in your body. Directly, we can address the $102 million market for developmental and reproductive toxicity, and we can immediately sell our products to agrochemical, industrial chemical, and pharmaceutical companies, spaces where drug development pipelines can span over 10 years, and even a 10% improvement in the predictive nature of toxicity-based failures can lead to tens of millions of dollars in savings per compound. So to summarize the value of our Rosetta Array platform, we have a human model of brain and spinal cord development that can be used to streamline and decrease the cost of drug discovery pipelines. We can also decrease the risk of releasing these drugs to the clinical market and therefore decrease the cost of drug development. And we can create personalized models for novel drug discovery applications. The team itself is composed of myself. I am a professor of biomedical engineering at UW-Madison and co-developer of the Rosetta Array technology. Dr. Gavin Knight is a former graduate student, current scientist in the lab, who also co-developed this as part of his thesis project. And Professor Rebecca Willett, we've collaborated with her for several years, and she is a professor of statistics and computer science at the University of Chicago, and she's essentially developed the AI algorithms that we use to analyze our tissue arrays. The Rosetta Array itself has been developed with over $4 million of funding from the agencies you see here. We have this is built upon over 3 different patents. This is built upon 3 different patents that have been filed by WARF and developed across 10 different publications. We have early collaborations with the EPA and other Fortune 100 companies, and we were just awarded a $1.7 million fast-track grant from the National Institute of Environmental Health Sciences. So NeuroRosetta itself, using the Rosetta Array platform, can provide contract developmental neurotoxicity screening to regulatory agencies and chemical and drug companies. We can provide the platform as a off-the-shelf kit that can be used by contract research organizations, and we can work with research labs and institutes in order to create personalized disease models and use those for precision medicine drug discovery applications. Again, my name is Randolph Ashton, co-founder and CEO of NeuroRosetta, and I am pleased to present to you our Rosetta Array technology. And currently, we're seeking corporate collaborators that can serve for beta testing our platform for their D&T needs. Thank you.
Good job. All right, thanks so much, Randy. Now, next up, we have Dr. Sandeep Gopalakrishnan. He's an assistant professor at the UW-Milwaukee College of Nursing, which is Wisconsin's largest nursing program. Let's hear more from Sandeep about the use of AI in revolutionizing the wound care ecosystem.
Thank you very much. Good afternoon, everyone, and thanks for the opportunity to introduce megaperceptron. And as you can see from the title slide here, what we are trying to do is predicting the wound healing outcomes with big data. And what we are is a multidisciplinary group of researchers coming up with a common goal of solving a significant problem in healthcare. So the question then is, what is that significant problem in healthcare? So we all get cuts and nicks at different points in our life, right? I can see Mike has a bandage in his finger. So cuts and nicks are pretty much common. And when we are having a normal healing cascade, you heal after a certain amount of time. But close to like 2% of the US population is unfortunate to have that normal healing cascade. And the reason is multifactorial. It can be because of their diabetic background. It can be because of vascular issues. It can be because of their aging skin, which is a fragile skin that is not going through the normal cascade of things. So there are close to like 600 million annual cases of acute as well as chronic wounds that happens in US, which burdens our healthcare system by close to $20 billion US. And on top of that, think about diabetic foot ulcers, individuals moving forward with amputations, and amputations happens every 30 seconds in US, and that becomes again a huge economic variable in the context of a burden as well. So we identified the problem here, then what is the solution for us? So as I have mentioned before, like there are a lot of individuals with chronic non-healing wounds. What are they going to do? They are going to see wound care specialist, similar to my colleague here, Dr. Jeffrey Nisgoda, who is a very familiar name in the wound care domain. So when Jeff sees a patient with a diabetic foot ulcer or a venous leg stasis or an arterial ulcer or a pressure ulcer, he does a lot of assessments, correct? He looks through the wound, he characterizes the wound, he measures the length and the depth of the wound to identify the volume. He does a lot of assessments in the context of its appearance, whether the tissue is necrotic, whether there is granulation tissue that predicts him to gauge the healing process, so on and so forth. And based upon all these manual evaluations, he determines what kind of intervention should be there in place that helps with the healing trajectory, correct? So the beauty here is that most of the assessments are done manually. So when you think that when Jeff does this versus when I do it versus when a third person in the clinic does it, there can be chances of a lot of inter-rater variability coming into the equation, correct? So the outcomes can be variable as well. So what we are trying to do here is that we are trying to automate the majority of the process that is involved with the wound assessment process. So we start with the data collection aspect of stuff, so we can automate different processes that is happening with the data collection. Simultaneously automate majority of the events that is happening with the measurement, whether it is with the 2D, 3D measurement of the wound characteristics. And obviously we can provide wound care clinicians with an informed analytics which can derive them high-level assessment of the diagnostic tool of it as well. At the same time, there is no prognostic tool that exists at this point of time, which basically says that if you do A, B, and C, the wound will be healing in X amount of time. So we are using data analytics to basically derive some of the prognostic measures in the context of healing trajectory as well. So our strength comes from our proprietary softwares, algorithms, as well as data sets. And as you can see from the slide over here, we have algorithms that localizes, segments, classifies, not only the tissue type, but the classification of the diagnosis. At the same time, the prognostic trajectory of the wound based upon the body map index, at the same time, the electronic health records. So we are comprehensively looking at the wound in the case in assessing it digitally to have this particular platform in place. Another strength of our data set is that it is a clinician annotated data set. So like many laborious hours have been put into annotating different types of images to basically feed into the machines to understand the different types of classifications that we were doing here. So everything is done in the cloud. So the interface is in the context of a cell phone, as you can see. The cell phone captures the image, captures the required data that is required for the machines to basically drive some of the processes of learning, some of the processes of predicting, so on and so forth. And at the end of the day, the machines will be providing, or the algorithms will be providing clinicians with an informed tool in the context of analytics to gauge the kind of prediction that is happening in the context of the wound healing. At the same time, it is a powerful tool in the context of the patient population as well that I probably will be discussing sometime later. So we have different competition in the market, as you can see, and our product at this point of time is convenient and more affordable to use when we compare to other market players as well. We have received significant funding, especially from the UWM Research Foundation and various internal grant mechanisms at UWM. Close to like $250,000 was received in various funding cycles, and we commercially partner with various other similar players in the market as well. So what we are asking here at this point of time, we have developed a platform, but we want to scale it up. To scale it up, we are looking for close to like $500,000 for the next 18 months. So what are we doing this for? We are trying to build infrastructure, collaborate data with other individuals who basically has access to data, hire AI/ML professionals, scale, and launch the platform to the next level. And we would like to see ourselves at the interface of various other digital platforms that are considered to be the next frontier of healthcare delivery, whether it is the delivery at home, integrated care, patient-centered care in nursing homes, or real-time monitoring of wound in the context of identifying different prognostic variables as well. Thank you very much.
Thanks so much, Sandeep. All right, next up we have an exciting pitch about hemp cultivars coming from the team at the UW-Madison's Wisconsin Crop Innovation Center, which is also known as the WCIC. Our presenter today, Mike Peterson, unfortunately couldn't join us. So I'll be giving his pitch about this first-of-its-kind technology coming out of the largest public and private crop editing and transformation facility in the United States. So the team at the WCIC is composed of highly skilled individuals, and together they have worked to develop the world's first transgenic hemp plant. This is a patent-pending technology that has the ability to advance hemp in the ways that the corporate world has seen for other crops like corn and soybean in the past few decades. The team has combined their experience to focus on hemp, which is a notoriously difficult crop to engineer, and that's because it has resistance towards common tissue culture techniques in the lab. But with their new technology, they have the ability to insert novel genes or edit existing genes in the crop. And this allows them to introduce new traits that can provide economic value to growers and new products to consumers. But if this plant is so difficult to work with, why hemp? Why did they decide to focus their efforts on this? Well, the cannabis market, and hemp is a species of cannabis, is a multi-billion-dollar market. But until recently, it had been subject to over 80 years of negative federal regulations. Those regulations made it nearly impossible for teams like the WCIC to make any significant advances in the cannabis space. But cannabis has over 50,000 uses, from anything from like textiles, clothing, food, building materials, and medical applications, just to name a few. And so with their technology, with genetic engineering and editing, they have the ability to open new opportunities by introducing new traits that can capture huge value in the market. For example, their technology has been shown to increase fiber biomass and yield. And this is important because there are big companies like Patagonia and Nike who are using hemp fiber to make their clothes and their shoes. There are other companies who are looking at using hemp to make carbon-negative building materials like hempcrete. Hemp itself has the ability to capture over 2 times the amount of CO2 from the air than trees can. And because of that, it will likely become a go-to crop for carbon credits. And so as industry ramps up its demand and its interest in using hemp fiber, the genetic engineering will be called upon to keep up with this demand, and by creating these crops that have this individual trait for increased yield. Another space in which this technology can have a lot of impact is that of the cannabinoids. In particular, this technology has the ability to increase or change the ratio of specific cannabinoids in the plant. So we all know about CBD and its potential benefits and uses, but there are over 100 other types of cannabinoids, more rare and potentially more valuable cannabinoids in hemp. For example, CBG is being looked at by the pharmaceutical industry for its potential medical benefits. It has 25 times the value of CBD, but it's produced in significantly lower quantities. And so with this tech, the WCIC team can ramp up the amounts of CBG or other potentially valuable cannabinoids in hemp to create value. Furthermore, this technology has the ability to customize or increase the amounts of key components in hemp to create new opportunities in the medical and the fragrance industries. These key components that I'm talking about are aromatic compounds known as terpenes that give hemp its flavor and odor. Now, these terpenes are produced in minute quantities in the plant, but they're still being explored for their medical benefits. And combinations of terpenes can be used to create fragrances. And so with this tech, customized terpene profiles or increased levels of specific terpenes can be induced in the plant to create high-value lines. So as I mentioned earlier, this team has extensive experience. They've worked with both public and private clients in the US and abroad. And the team consists of Mike Peterson, who couldn't be here today, a senior scientist at the WCIC and an inventor on this technology, Sean Kepler, who's the director of the WCIC, a crop breeder and a co-inventor for this tech, and Shelby Ellison, who's an assistant professor of horticulture at UW-Madison, whose research program focuses on hemp genetics and breeding. She is also the point person for UW's industrial hemp and research education. Now, this technology has received traction so far. The team has been able to apply the methodology to create proof of concept plants that can express a red fluorescent gene. And they have been working with industry clients, Hypercan and ZCal, to find traits of interest that can boost their product pipeline. Additionally, they're focusing on addressing the needs of cannabis producers by controlling the cannabinoid production, and have successfully developed plantlets that can target specific individual traits. For example, they have developed a zero THC line, an increased CBG line, and a line with increased trichomes. And they have received over $2 million of funding to date from various sources such as the Erdman Family Farms, USDA, and WARF. And all of this money is going to help further develop this patent-pending technology and introduce value-added traits into hemp. But there are numerous other traits that this methodology can be applied to. Traits like disease and drought resistance, seed resiliency, fiber output, growth habits, and more. And so the team is looking to find industry partners to work with them to identify traits of interest for commercial cannabis growers. And also they're looking for collaborators to work with them and the UW-Madison to help grow and commercialize hemp for the global industrial hemp market. So thanks so much for listening to me give someone else's pitch today. If you have any questions about this technology, please feel free to email Mike, or you can feel free to email me or anybody at WARF, and we'll help put you in contact with the WCIC team. You have to hear a little bit more from me. So next up, we have Dr. Adhira Sankara, who's the assistant director at WISIS. She's going to be presenting a technology coming from UW-Platteville in its well-renowned civil and environmental engineering program. So let's hear more about health monitoring and imaging systems for concrete structures.
Great, thank you. Thanks, Leslie. So thank you everyone for being here, and thank you to WARF for giving us the opportunity to present. As Leslie mentioned, this is a technology that was invented by Dr. Hanwan Jiang from UW-Platteville. My name is Adhira, and I'm the assistant director of WISIS. And for those of you who don't know, WISIS is a nonprofit that's dedicated to fostering innovation, research, and entrepreneurship on the 11 UW regional campuses, including UW-Platteville. So this technology addresses the problem of America's decaying infrastructure. This is a $123 billion problem. As you can see from this picture, it's a recent bridge collapse in Pittsburgh, Pennsylvania. The toll of decaying infrastructure is more than just a number. It takes a toll on human life, it disrupts society, it disrupts the way we function. Infrastructure is a key component of our modern day life. So 39% of the bridges in the US have exceeded their design lives. And we know this is a big problem and something that's getting a lot of attention now with the $1.2 trillion Infrastructure Investment and Jobs Act that was announced relatively recently. So why is this a problem, right? I mean, we've had roads and bridges for centuries, really. So why aren't we better equipped to test them, to monitor them, and to avoid the kind of bridge collapse that happened in Pittsburgh? Well, part of the reason is that the current solutions are inefficient. So state departments of transportation rely primarily on visual inspection of bridges and roads. As you can imagine, that is not a very robust data set that you can get, right? They're literally just walking around under the bridge and looking up at it. So why is it that, given all of the advancements in sensor technology, that this isn't being implemented, right? Well, the problem is that current testing methods are expensive. They require extensive technical training, and more importantly, they disrupt traffic. As anybody who's been on a bridge knows, you do not want to shut down a bridge for a day and a half to test the cracks on it. There's also no regulation that mandates testing of these bridges. And the complexity of the post-processing of the data is also a big barrier in terms of the cost and time and effectiveness of these technologies. I really like this quote from the Pennsylvania Department of Transportation because it sums up the problem beautifully. So this was from a recent survey that was conducted by the U.S. Department of Transportation's Federal Highway Administration. And most of the states in that survey were interested in improving their testing methods and the frequency with which they tested. But as this quote says, uncertain accuracy in the non-destructive testing results and the time and costs involved to get final results are the main barriers to implementing NDT, which is non-destructive testing, on bridge decks. So what are we going to do about this? Well, this new technology that's coming out of Platteville, it's an ultrasonic monitoring system that is aimed towards solving some of the pain points that are associated with regular monitoring and testing of infrastructure and concrete structures. So by combining sensor technology with an ultrasound signal generator, multi-channel data acquisition, and proprietary data processing algorithms, the interior conditions of any cross-section of a bridge, or really any concrete structure, can be visualized three-dimensionally. So with this technology, small stress changes on the order of 0.1 megapascals and cracks as thin as the human hair can be detected. But more importantly, the advantages of these technology is that it can assess full-size, large volume structures. It has high sensitivity, and it can provide real-time three-dimensional images, at least to a certain fidelity. So what this means is that it can be used on in-service structures. You don't have to shut down the bridge to test and use this technology. It is also a platform technology, which I'll get to in just a second. So this technology has been developed, tested, and validated. A fully functional prototype system has been developed in the laboratory and field tested at the, I'll try to say this, it's a little bit of a tongue twister, at the Berwick Bay Bridge in Louisiana, which is a vertical lift bridge. So they tested this technology and compared the results with kind of the existing standards of testing, and the results were incredible. I mean, they were able to get a really accurate health assessment of this bridge, and they were able to do that without shutting down the bridge. In fact, they could see how the bridge was reacting when a car or a truck drove over it. So, as I mentioned, this is a platform technology. The non-destructive testing market is a $25 billion market, estimated to be $25 million by 2026. So some of the other applications where this can be used is oil and gas pipelines, power plant inspections, aerospace, mining, and even something like lithium-ion battery health monitoring for our electronic vehicles. So what we're looking for with this technology is partners, industry partners, or startup founders who are interested in bringing this technology to the next stage and really implementing and validating the market piece of this technology. Our inventor is still very much involved. She's no longer in the UW system, but she's willing to assist with any technical development and any future development that might be necessary for this. So if you're interested in this technology or connecting with the technology and innovations that are coming out of the other 11 UW regional campuses, please contact me. And I'll also put in a plug. We are having our annual conference this summer at UW La Crosse called Spark 2022. So if you're interested in attending, it's a showcase of all of the innovation that's happening across the state. So thank you very much.
Thanks, Adhira. All right, finally, let's hear from Kieran Furlong, who's the CEO of Realta Fusion and an honorary fellow with UW-Madison's College of Letters and Sciences. Kieran will be telling us about the breakthrough physics technology that is being developed for viable fusion. Take it away.
Great, thanks very much, Leslie. Good afternoon, everyone. I'm Kieran Furlong, co-founder of Realta Fusion, along with Professor Kerry Forrest, who's here. Give us a wave, Kerry. A prior WARF Innovation Award nominee. Realta is an early-stage startup spinning out from the University of Wisconsin-Madison, developing the lowest capital and least complex path to fusion energy, to commercially competitive fusion energy. So why, you ask, might you care about that? Well, let's start with the biggest problem facing all of us today, climate change, because we aim to play a large role in solving it. We're laser-focused on getting to a first commercial fusion plant by targeting the need for low-carbon industrial process heat. So let's put that need in context. Over 80% of our primary global energy supply still comes from fossil fuels, and even best case projections for a net zero future still have that share at over 70% in the 2030s, and that's while we continue to grow our global energy needs. So while transportation tends to get most visibility, if we want to arrest climate change, we really need to focus in on industrial energy use. So industry consumes almost half of our global energy, and 2/3 of that are actually used to generate process heat. So the world absolutely needs an alternative source of high quality heat to tackle climate change. So where are we going to get that? Well, let's look to the sun. Now some of you might be thinking solar. Well, that's, probably what you're thinking is not what we're thinking here. We're thinking about the reactions that power the sun, which is fusion. So we will aim to harness fusion reactions here on Earth. Quick primer on fusion, as it might be new to some of you. But essentially what we do is we heat two different isotopes of hydrogen, deuterium and tritium, to extremely high temperatures to get them to fuse together and produce helium and neutron and a lot of energy. Just a few grams of these isotopes would provide each of you here with literally a lifetime's worth of energy. So we believe fusion is the solution. However, current fusion projects are taking too long, they're too capital intensive, and are too complex. Realta is developing a reactor, the Hammer, that will be a much better fit in terms of time, capital, and risk for the early adoption of fusion energy. We're applying advances in superconducting materials, plasma physics, and computing power to a simpler linear fusion configuration. This is a high magnetic field compact tandemer reactor consisting of two very high field end plugs, which you can see highlighted in red here, on either end of a central cell plasma that can be expanded modularly for increases in power output. Our overarching aim is to build the first of its kind fusion energy plant. Therefore, we're extremely focused on finding the ideal combination of application and partner to build plant number one. While grid scale electrical power generation is part of our long-term plan, we believe the first plant will be for industrial process heat. For example, we're exploring the refining and petrochemicals market. The energy used for process heat in the chemicals industry is a market in the tens of billions of dollars. How many tens of billions depends upon kind of the daily price of natural gas, which typically sets the scene. And also the players in this market are attractive to us because they're really deep in engineering capability and are used to the large CapEx projects which this will require. So we think they'll be able to successfully deploy a fusion energy plant. If we look at costs, there's always the concerns with novel energy sources. Well, it's just going to be twice the cost of what we're currently using. So an independent estimate of the cost at scale for our energy has put it at $7 a million BTU. Don't worry about the unit, it's just what they use. Right now in the US, the average for this month has actually been around $8.70. So this would already be competitive with current energy prices. And that's here in the US where we've got cheap gas because of the shale boom. If you're looking at importing LNG to the EU or spot Asian markets, we're well below what those markets are paying for energy. Burning fossil fuels to generate all of this process heat also emits huge amounts of carbon dioxide, so 1 gigaton of CO2. To put that in context, that's equivalent to the total CO2 emissions of the UK, France, and Italy combined. So if we can come up with an alternative source of heat that works for industry, we can decarbonize, for example, the chemical industry and have a material impact on global greenhouse gas emissions. We're assembling a team of experienced innovators, each of whom bring a necessary piece of the puzzle we're solving. Kerry over here is our technical lead and has deep experience in plasma physics. I, Kieran Furlong, have a background in the chemical industry and have spent the last 15 years in clean tech startups and venture capital, bringing new sustainable technologies to market. Jay specializes in plasma heating and stability. Ben brings blanket design experience from next generation fission reactors. And Oliver is at the cutting edge of plasma-facing materials technology. As we identify the initial application, we'll build out and expand this team with experts from those fields. Our technology development plan has 3 main phases, and we're in the first of those right now, which is our WAM machine. With the learnings from our initial WAM machine and the successful demonstration of our novel magnets and heating systems, we'll move into demonstrate deuterium-tritium steady-state operation in phase 2. In the third phase, we'll build the first end plug of a semi-commercial scale reactor and progress to the full tandem Mir hammer. All of this is directed towards developing a fusion technology that's right-sized for private sector adoption. In short, reducing size and simplifying reactors will make fusion more viable. WAM 1.0 is funded by RPE with support from WARF, the University of Wisconsin-Madison, and Commonwealth Fusion Systems. We anticipate raising 80 to 100 million over the next 2 to 3 years, matching our capital raises to significant risk reduction milestones. We will be raising our seed round later this year, so any of the investors in the room, happy to take a card or talk to you about that if you're interested. In summary, less complexity, less capital, and therefore less risk. This is Realta Fusion. Thank you.
Outstanding? Weren't they absolutely outstanding? Inspiring research taking place here in Wisconsin across universities. Thank you, all of you, for just really doing a remarkable job. I know we have a lot of folks who are going to have questions. We're going to be transitioning our space right now. My friend Mallory and Jane, they're going to come right on up. They're going to create a little bit of a horseshoe with these chairs behind me. So we'll take just a moment to do that. While we're doing that, I'd ask you to take a moment, jot down the questions that you've got for our pitch presenters. Our panel discussion will provide an opportunity for you to ask those questions, and we'll be happy to get you the answers to those questions. So you're so efficient. Thank you so much. Awesome. At this point, I'd like to introduce our great friend and colleague, Nii, co-founder of Meriton Partners and the moderator of our panel today. Nii is going to be taking questions from the audience, both in person as well as virtually. If you are in person and you have got a question, just raise your hand. Nii will call on you, indicate who it is that you'd like to direct that question to, and go ahead and ask it. She'll repeat your question so that we can make sure that our audience out and about around the world also hears it. If you are attending virtually and you want to ask a question, please put it in the chat, and my colleagues will write that down and make sure that it gets up to Nii. So Nii, it's all yours.
Oh, I didn't mean to do that. Hey everyone, I guess we'll bring the presenters up. And I'm just here for the song and dance part, so. I'm going to scoot closer and get close, and I hope that's okay. All right. So we'll go ahead and kick it off. But before we do, I got to echo what Janan said. That was absolutely fantastic, and thank you so much for making very, very complicated concepts very simple to understand for dunce caps like me. The other thing is I'm very impressed, and I don't know if y'all are, but I'm very impressed with Kieran's ability to make somehow a very complicated concept break down to the acronym HAMMER. So. All right, so let's go ahead and kick it off. I'm going to go ahead and start with a question while y'all are kind of thinking through your questions. This first question is directed to the professors on this panel and the researchers on this panel. So with the end of our panel here, with as much renown as you have in research, why are you spending part of your time in commercializing your research? And let's go ahead and start with Sandeep.
Yeah, sure. So we never envisioned to commercialize this particular study, and it all started as a fascinating academic project, and our goal was to do this study and publish extensively, so on and so forth, similar to any other researchers. But as we started publishing our work, we gained significant traction from the industry, and we started getting communications with respect to collaboration and sharing our algorithm and data sets as well. And still we get a lot of inquiries regarding sharing our data sets. And we do that generously as well, but the rest of the world out there doesn't do. But so we found that there is a significant gap there in addressing with respect to data that we have. So we found the potential of having a commercial entity when all these inquiries came, and our co-founders discussed about this, and we found that it is the right time to incorporate, and we did that in the middle of the COVID pandemic as well. So, okay. So that was the whole premise behind the commercialization of our platform.
That's quite a bit of a pull to be taking a step away in the middle of a pandemic to launch a company.
Yeah, because most of the data science work can be done remotely, right? So I don't have to go to the lab to do the stuff. So we use that time to basically leverage this and move this forward.
Great. Randy?
Yeah, so in our space, sort of creating these models of the human brain and spinal cord development, that field has been around for about 15 years now. And I was at the forefront of that in my PhD studies, and now have a lab that sort of pushes that forward. But what we saw was that there was really a gap between what's being done in the lab and utility of that technology, largely because it's hard to scale that technology. And so as an engineer, my lab has been working for years to figure out how can we take this technology that we can do in the lab, create all these wonderful models of human neurological disease and come up with various compounds and treatments, and actually create that and turn that into a platform that can be scaled. So you can use it for regular regulatory applications as well as the drug discovery applications. And that need has always sort of fueled the research. And now that we have a way to do that, we wanted to basically provide that technology to the commercial and regulatory markets so that we could potentially, decrease neurological disorder burden, as well as be able to increase the safety of the thousands. This was really something new to me that I learned as I became more engrossed in regulatory science, and you would think that all the chemicals that are out there, which are on the order of 80 to 90,000 that are in the commercial market space, they would have data for this, but they don't. They basically put it out, wait for something to occur, if they can trace it back to those compounds, and then remove that compound from the market. And so there's this sort of open-ended question of how much of the chemicals that we just can't correlate to these diseases are currently out there, and the reason why we're seeing these increases in neurodevelopmental disorders and neurological disorders as a whole. And so we think this technology really can address that question, and that was the motivation for pushing it out there. We had interest from various agrochemical and industrial chemical companies, and so we decided, we should be the ones to help to push it out there.
Great. It sounds like almost a recurring theme between Sandeep and Randy, in that people were interested in, and there wasn't another way to get it out there unless you did it yourself. Mike?
Sure. Well, if you think about over the last 50 years, computers and electronics have revolutionized our lives. And they've been getting exponentially better over time. So if you even think back to the 1990s, how feeble computers were and how great they are now. But that exponential improvement is ending because of the limitations of materials. And so one of my life dreams is to invent new materials for electronics so we could continue that exponential improvements in computers, and it's impacting every part of our lives. So,
in the world that you live in, you have spent easily 10 to, I'm assuming some of you are like 30 years old, so 10 to 12 years. in research, doing the work that you're doing, for you to take the time away from publishing and getting more grant funding to go into a world that you don't know just because the world needs the solution that you're providing. It's really admirable, so thank you for that. All right, I'm going to see if anybody's got any questions. Yes.
Yeah, to the academics, amazing. This just gives me so empowered. So thanks for your work. You've been in industry for so long, and so I guess my question is like, in your space, was there an aha moment that each of you had? Because a lot of startup founders have those aha moments where I was doing X for so long, and then an aha moment happened, and life is never the same. I'm just curious if you've had an aha moment being in the industry for so long. I'm curious to hear that.
So I'm going to reiterate that question. So that comes from Matthew Key. The question is, for those who have been in the industry for a long time, have you had an aha moment, and what was it? So let's start with Kieran.
Oh, okay. I thought it was going that direction.
Yeah, you can go too. But I'm just
I think it was directed towards the
industry,
academics.
Like studying and researching for so long.
Oh, my apologies. That's a moderator. Ooh.
That's great. I love it. That's good.
So I can go. So the aha moment in the academics, or when we transition to the industry, it wasn't
The
clear.
aha moment that was like, yes, I need to do this. Like, yes, I need to start this company. That was that aha.
Yes. So as I have earlier mentioned, so with the data science projects, data is the key thing, right? So when you play around with data and when you are asking people to share the data, and if they are not doing it, and if you are trying to find your own resources to, especially local resources to gain that data to do your work, and somebody, for example, somebody emails me and asks, can you share that data? At that point, you understand that how valuable what is in your pocket. So that basically helped us commercialize, and probably that was the right tipping point where we thought that it is the right aha to move forward.
Randy?
Yeah, I would say on my end, as an assistant professor, I'm now past that stage, thank God. You're constantly searching for funding. And so I was recommended to apply for this Innovation in Regulatory Science Award from the Burroughs Wellcome Fund. Really prestigious award. Basically last minute they told me I should apply for it, and so I blew away a weekend writing the proposal and submitting it. To my surprise, it was awarded. And from that experience, going to the conferences for the people who win those awards, I got a really good introduction into regulatory science and what is needed out there. And at that point, the developmental neurotox world, I hear it at that conference and every other conference I've gone to, that they really need good solutions for being able to assess the risk associated with these compounds. And so on the lab side, Gavin, who's here today, a former graduate student and postdoc, he had been working on this solution. I said, these two marry, and we could really provide a solution that could help out society, regulatory agencies, and companies alike, right? And so it was really just marrying the two, and then saying, okay, well, I have an engineering background. We should be able to scale this. That's what I'm trained to do, and that's exactly what we did. So that was the aha moment where we basically were past the point of sort of very fundamental technology development to say this works, and we know this works well, and now we just need to provide it for a commercial scale.
Mike?
Sure. Yeah, I think for me, when I kind of realized, hey, the world needs a solution, the microelectronics industry needs a solution, and my lab is the only one in the world doing it. They need our technology. That's kind of like the aha moment. You kind of like when you're young, you kind of think, oh, someone else is going to figure out all the world's problems. But then really you figure out, hey, you have to solve at least some tiny fraction of the world's problems.
So thank you for that question, Matthew. I think I'm going to move on to a question that's sort of related to the people we haven't heard yet. So Kieran, this question is for you. You have a lot of years of experience as a global VC. As an investor, you've seen a lot of companies in a lot of different markets. What is your aha moment when it came to Realta and Carey?
Yeah, interesting. So like I've mentioned in my talk, I've been working on sustainable technologies for at least 15 years, and really interested in, that's why I left the corporate world, because I was in a world where that wasn't top priority. So I've been doing this for a long time. Global warming is a huge, huge threat for us. I'm not going to go as far as to say it's an existential threat for humanity, but it's definitely going to make our civilization a whole lot more unpleasant to be part of as humans. So there's this big, huge need there. And in fact, when I first talked to Kerry about fusion, it wasn't so much the aha. It was more like, are we really going to need this? I mean, 2050, by that point, won't we have sufficient wind and solar, sufficient distribution, backup energy storage to smooth out the duck curve and all this kind of stuff? But the more I got talking to her, the more I realized, absolutely, yes, we are. The more I looked into it. As you saw kind of from the talk, like there's a huge amount of energy used for process heat generation. Turning electricity into that high temperature heat that's used in industrial processes, not a very efficient way of doing it, not a very good way of doing it. So that for me was like, well, here's a huge application, a huge need that we need to decarbonize, and there's not very many other options there. But neutrons carrying a whole bunch of energy that you can convert to heat to use for this, that was it for me. It was kind of like delving into the drawer of my long ago career and saying, hey, I used to work in that world, lots of heat needed, where are we going to get it from? So that was the real kind of aha for me around why would I go. And from fusion, it's a case of, yeah, we need it. I think the rest of the world is finally waking up as well. So I'm sure there's others in the room who've been passionate about this for a long time. But I think last year with the IPCC's 6 report, and with the more and more corporates are now looking at net zero targets and so on, it kind of feels to me, at least, I'm being an optimist here, that the world is finally waking up and we're focused on these things. And there's going to be more pull for something like fusion, which so far, I always go back for the 70-year history of fusion, was mostly an academic curiosity, the kind of thing that physicists in Los Alamos and University of Wisconsin-Madison and so on got excited about, but the rest of the world kind of treated as, yeah, that's all science fiction, quite literally. And I think now we're actually seeing, you open the pages of Popular Mechanics, there's an article on fusion every other month kind of thing. It's really gathering steam, and there's reasons for that too that I can talk about in a bit if you wish.
Okay, and we'll come back to that. We'll come back to the timing for why now is a prime time for fusion. I want to ask that question. I want to expand on that. So there's a lot of other researchers working on fusion. Why Kerry? Because founding a startup company is like getting married. So. It
is. Well, and actually here's some credit to WARF. So WARF essentially did a bit of an arranged marriage here and partnered us up, which was a new way of using the accelerator program at WARF. But it really was a case of, well, hey, Kerry's got this, had won this massive award from RPE, a $12 million project that there's just oodles of work that he's doing on the technical side, but a significant part of what RPE are focused on is the commercialization aspect. So they call it T2M, or technology to market. And WARF had said, hey, Kerry, would you like some help on the tech to market side of things? Yes, okay, we've got this guy Kieran, you've already met him back in the university, kind of when I used to work there. Why don't you get together and start working on the T2M, the tech to market deliverables for the project? With the kind of unspoken, I would say, but definite intent of, well, hey, if this works out, we've got the business guy, we've got the technical guy, let's see if there's a spin out that's going to come out of there. And luckily, we seem to have hit it off sufficiently to the point where we're willing to get married in startup world. So that's where we're going.
Like most good matchmakers, we don't invite you to go on a date. We invite you to dinner as a group. Great. Let's move on from the personal motivation and deep dive into the technology a little bit, if that's okay. This question goes to Ed here, and this one it came through our live stream. Someone seems to be very interested in taking your technology and figuring out what to do with it. And their question is, what is the commercial and technical readiness of this technology, and when and how fast can I get my hand on it to deploy?
That's a great question. I think people define commercial readiness in a different way, so I'll kind of lay out the facts of where the technology is. As I mentioned, it's been field tested, right? So they've actually put it on a bridge, they've tested it, they've driven vehicles over it while it's in progress. The data looks really good. The algorithms are there, the data analysis is there. You can see in real time what's happening on the bridge with these sensors while cars are driving over it. So on the technology side, I think it's as far as a university or a researcher can take it. What we're looking for now is an industry partner who will be able to kind of validate it more on the market side. There might be a little bit more on the technical side as well as kind of productizing it, right? But it is a fully functional beta product, let's call it.
Great. From what,
yeah.
so just an expansion on that, from what Adhira described, in ranking technologies, how ready technologies are in terms of commercialization and technology readiness, the highest that you can go is a 9. And what you've described is pretty much a 7. And 7 and 8 is the point at which a technology can be mature enough for somebody like the Department of Defense to want to scalably adopt that technology. So that sounds really mature.
I'll also add that, with the infrastructure bill coming up, we're also interested in collaborating or partnering with industry for grant programs, right? So grants that are more on the market readiness side, or the last stage of, as Kieran was saying. So that's also an option that we're open to.
What does a collaboration like that look like?
That's a good question. I think it depends a little bit on the granting agency and what the grant is, but I think this is in a really good place for like an STTR type of or SBIR or STTR type of a grant award, or any of the infrastructure bills coming on, where we might be able to kind of expand on the implementation and testing. And also test this in other, as I mentioned, the platform technology is, we can test it, we've tested it on bridges, but also roads and some other solid concrete structures. So the partnership would be between, we would be able to license the technology out to a startup if they're interested, and then they would do a lot of the market validation piece of it, find pilot customers, implement initial projects, things like that.
Great. And then a continuation question from that same attendee is that, what is needed in terms of new equipment, process, and time to set this up, and then how long will it be before you can get results?
I'm assuming that when they say get results, you mean results on the, the quality of the bridge, and not results on the, the startup. But so the nice thing about this is it actually kind of incorporates into the workflow that currently exists. So, currently people go up, they put these sensors all over the bridges, and that is a little bit of a tedious process. We could potentially, change things there, but it fits into that workflow where these sensors would be implemented, deployed in a similar way to what's currently done. The nice thing about the post-processing piece of it, though, is that you get that real-time response or real-time feedback about how well the bridge is doing, but then also it reduces the amount of post-processing that needs to happen. It also reduces, because it can do it on a large scale and with a higher accuracy, it reduces the number of steps you need to do. You can deploy this on an entire bridge in one day, as opposed to some of the other technologies, the destructive ones, where you have to to get this accuracy, typically you drill a hole and you insert a sensor, and you can only do that in small sections of the bridge, and you kind of move along. With this one, you can do the entire bridge, and you can do it faster and more efficiently and get the same or similar levels of accuracy.
Something that strikes me about this technology that I didn't fully realize until you said drill a hole in a bridge is that if you're testing to see if there are cracks on the bridge, you got to go drill a hole in the bridge. It seems counterintuitive to me. So,
yeah.
Great. So your technology eliminates the need for that, which seems pretty helpful.
Correct.
For extending the life of a bridge. Let's move on to a question that's sort of similar and related, and this one goes to Mike Arnold. So you have an aligned carbon nanotube method for creating these aligned carbon nanotubes. How does that integrate with existing semiconductor manufacturing equipment and processes?
Sure. So right now, when you start with a silicon wafer, it's just a pure piece of silicon that's polished, kind of like a mirror. That gets input into a $1 billion fab, maybe seen on TV commercials, Intel commercials of people wearing these bunny suits working in these very clean fabs. And then from there, many steps of fabrication happen to turn that piece of silicon into a computer chip. So our technology will place nanotubes on top of this silicon wafer, And then they'll more or less be drop-in replacements that could go into these same fabs. So we don't need new billion-dollar fabs, which is very important.
And to make the aligned nanotubes on the wafer, can you make them in the existing facilities that already exist?
Yeah, so we would need to retrofit the facility with our solution process method, but then yeah. So you could modify the silicon wafer very inexpensively with our two methods that we've patented. And then that would plug in to be a drop-in replacement into these fabs.
Great, thanks. This next question goes out to Randy. So you briefly mentioned that your method, in order to make these organoids, you take cells and you put them on your plates. And then those cells, through your proprietary method, becomes the model that is a mimic of the human brain and spinal cord. Where do those cells come from, and what cells are they?
Yeah, so that's an important part. We get these cells from adults. We can genetically sort of revert them back to a early embryonic state, but the source comes from adults, and then they can recapitulate the developmental process in our pipeline.
Great. And then there was a part in your presentation where you talked about personalized medicine. How do you get personalized models?
Yeah, so if you have a genetic background that predisposes you to a neurodevelopmental or neurological disorder, then as a patient, you can essentially now donate a blood sample, and those can be reverted back to your own, we call them induced pluripotent stem cell lines, and then we can directly take those lines and create a model of your human brain and spinal cord development. And so what that does is it places your genetic background within our model so that we can understand how you specifically could be predisposed to various risk factors that come from chemical, drug, and pollutant exposures.
And then an expansion on that question then, and this might call for you to speculate beyond the scope of your presentation, how long does it take if I wanted to get a model of mine and get screening done? How long is it from when I give you my blood sample to when your test tells me if I'm predisposed to something, if I'm exposed to, I don't know, tobacco?
So yeah, I mean, this depends on exactly the problem that we have, but essentially our pipeline, one of the big advancements we've had is to make this off the shelf. Essentially, once we have the iPSC lines, which can be a 2-3 process if you go to a hospital like the one at Madison. Once we have those lines, we can essentially make a bank, and then to do the screening that we do in our platform, we simply take frozen cells and put them right on our culture substrates. We then generate these tissues within a week, and so the screening process essentially occurs in parallel over that week time frame, and then we can start to assess your own potential risk for various compounds. Now, if you have a disease that shows up as a phenotype or a pattern within our assay, then we can actually see that as well within a week, and we could potentially screen known FDA-approved drugs to see if there are drugs that can be repurposed to actually try to get rid of that pattern or phenotype that we have in our assay, and then those could be novel therapeutics that are personalized to your particular condition.
Great. I'm going to see if there's any questions in the audience. Yes?
I have one for Mike. Mike, do you think that carbon nanotubes will accelerate the reality of quantum computing?
So this question, I'm going to just reiterate that question. This question is for Mike, and the question is, will carbon nanotubes accelerate the reality of quantum computing, sorry.
I would say probably not. So quantum computing and conventional computing are different tracks. And so what nanotubes will enable is orders of magnitude improvement in conventional computing. So we can bring it closer to what quantum computing might be able to achieve. And even if quantum computing takes off, it's not going to replace normal computing in most applications anyway. So we need faster conventional computers no matter what.
Yes?
Can I ask a related question to Mike? You said you can switch them. How do you switch them? Is it magnetic?
So I'll reiterate that question. So the question again goes to Mike, and the question was, you said that you could switch them. How do you switch them?
Right. Yeah, so the semiconductors can switch between insulating and conducting states. That's done with an electric field. So you apply a voltage nearby your semiconductor, but that voltage you're applying is not actually touching your semiconductor. There's an insulator in between. And that builds up electrical charges in your semiconductor, so there's very few of them or a lot of them, and that makes it either insulating or conducting. So it's called the field effect. So it's not a magnetic field, it's an electric field.
Similar to silicon.
Similar to silicon. So the physics are very similar. It's just that nanotubes are way better semiconductors than silicon. That's the secret to it.
You're welcome for that bit of a lecture. We'll send you a tuition bill. All right, question in the back.
This is a question for Randy. So how does the cost of your high throughput screening compare to like current market high throughput screening?
Yeah, so I didn't have enough time to put this slide in there, but essentially the current way that we do developmental neurotoxicity testing outside of animal testing is that you have a battery of different assays that you can do, which basically deconstructs the tissue development process to different sort of cell proliferation, cell viability, et cetera. And so there's a handful, roughly 9 or 10 different assays that you would have to conduct a full developmental neurotoxicity screen. Our particular platform streamlines that and takes at least 5 to 7 of those assays, depending on how you're looking at it, and makes that one particular assay. And it does it faster, and we can get the data back with less cost, significantly less cost. So I don't have a quantitative number for you, but just looking at that sort of fundamental layout of how that works, it would be significant cost and time reduction.
Okay, thank you.
Additional questions before I keep going? All right. On the timing side, we've talked about timing a lot, and I told Kieran I would come back to this. So you're on the spot again, Kieran.
All right.
All right. Why is now, right now,
For fusion?
the time for fusion?
All right. Well, here's an analogy that I'll use to explain it, right? If we think back to the Kitty Hawk moment, when the Wright brothers had the first powered flight, that was the culmination of a bunch of adjacent technologies and developments, right? So if you think back to the 19th century, there was plenty of aspiring aviators leaping off cliffs to an ignominious end with, man-powered wings and so on. Why didn't that work? Well, human power is not good enough to keep you aloft. I'd love to have a, flying bicycle, but unfortunately they don't exist. The Wrights were bike mechanics, by the way, in case you didn't know. So human power wasn't enough. What were people using for motion power in the 19th century? Steam engines. Can you imagine getting one of those 19th century steam engines to fly? Also not going to work. So you're in this gap in between stuff that's too heavy or stuff that's not powerful enough. Well, Titusville, Pennsylvania, in the latter half of the 19th century, struck oil. Okay, that's where we started the oil industry. You've got Rockefeller and Standard Oil come along, distilling the crude black stuff that's coming out of the earth for kerosene for lighting, but they're left over with this waste product called gasoline that some of the inventors of the time were like, well, hey, we can use this as fuel in this other new invention, the internal combustion engine. Okay, so you've got these adjacent things, the oil industry, the internal combustion engines were coming along, and that's what allowed powered flight. The Wright brothers, ingenious, fantastic mechanics and engineers, no doubt, but they were able to avail of these other technologies whose time had come. With fusion, the concepts have been around for a long time, right? But now we've got these adjacent technologies. One, for example, is superconducting materials that can provide much, much stronger magnetic fields. So essentially, when I talked about very high temperatures that we're trying to get these isotopes to, we're 10 times hotter than the center of the sun. So how do you put that in a vessel? There's no material on Earth that can deal with that. MC Hammer joke, you can't touch this. So it's like, how do you confine it? We're using magnetic confinement, but you need really strong magnetic fields to do that. So that's one advance that's come over the last few decades. Computing power. What you're trying to do is actually model what billions of particles are doing inside these reactors, right? And you're actually trying to apply little motion equations to each of those. You need massive computing power to be able to do so. That's an advance, right? That we've been talking about already here this evening in being able to use that computing power. So you've got these adjacent technologies which are being applied to the advances in plasma physics, which mean it is now on the technical side. And then, as I mentioned earlier, I think the pull is there as well. People are really beginning to cast around and say, okay, we need to decarbonize. You know, BlackRock and Vanguard and the pension funds are saying, what's our long-term decarbonization plan? Well, they need to go out and look for some of these large public companies. So I think you've got the pull factor is coming along with those adjacent technologies, and it really is a moment for the likes of Kerry, who've been working on this for decades, to shine, right? So, you know, there's hotspots of fusion research around the world, and we happen to have one of them right here in Wisconsin, in University of Wisconsin-Madison.
Shine like the sun.
There you go. Okay. You got any wham jokes in there too?
That was your subscription to the History Channel and the Comedy Central. So I want to ask another question on that. The fusion, for those of us who don't know about fusion, is that dangerous to human health?
Right. So this is actually, when I look at the adoption of fusion, we talk about this. Well, what are all of the hurdles we have to overcome? Scientists and engineers will instantly gravitate to, well, what are the technical challenges ahead? This is hard stuff. When we're all talking about really, really high temperatures, you've got really, really cold superconductors. It's very challenging technically. For me, actually, the biggest challenge is ensuring that all of us, humankind, actually can accept fusion energy as the way forward. To be honest, we could have solved global warming by now if we were to go out and use, nuclear fission as a way to provide all of our energy and electrify almost everything we could. That brings with it, though, a whole bunch of risks. Proliferation of nuclear weapons being one of them. The risk of runaway reactions being another. Risk of runaway reactions, not possible in a fusion system, because we actually have a lot less stored energy within the reactor, and the minute that plasma bubbles out and touches the side of the reactor, it just essentially quenches the reaction. So unlike a fission reaction, which will continue and build, this one actually is self-quenching. So that's one of the things, it's a lot safer. You don't think about the 3 Mile Island, that kind of stuff when you're looking at fusion. Proliferation, likewise, we're talking about taking hydrogen isotopes. Your end product is helium. You're not left with, plutonium or some other thing that could be a weapons-grade material. Additionally, the products with nuclear fission technologies, you've got long-lived radioactive waste. And understandably, people get worried about that. As an engineer, and having looked at the problem, I think we can handle that problem. We've got much bigger fish to fry when it comes to problems facing us all. That one could be handled, but I can understand people being concerned about it. Right? Where I grew up in Ireland, the very southeast corner, that was going to be the first place where they were going to put a nuclear plant in. My parents and their generation said, no, it was kind of the no nukes, Petra Kelly era. Didn't happen. I think with fusion, we really want to get in front of people, engage with communities, engage with people, and explain to them what fusion can do, what are the benefits. Undoubtedly, there'll be some risks that we'll figure out as we go along, but they're nowhere near the kind of risks that people associate with nuclear fission. And listen, it's going to be way, way better than what we do when we burn lots of coal and create localized air pollution and the damage that does on our health and our environment. So I think all in all, there's a much clearer path ahead, much safer path. Will there be issues that we're going to come across? For sure, but so far things are looking pretty good.
I'm going to go open it up to see if there are any additional questions before I take. Yes.
What about your feedstocks? Is it limited or?
Sorry, the question was what about your feedstocks? Is it
feedstocks for fusion, exactly. So we have lots of seawater on this planet, so I think we're going to be okay. So that's where we're going to get these, these isotopes. Essentially, if you've got water, you can get your deuterium for sure. Tritium is a much shorter half-life, so it's not as prevalent in nature here on Earth. And what we will plan to do is breed the tritium in situ for use in the reaction. So typically that would come from lithium, and now everyone's going to get worried about, well, lithium, don't we need that for our Teslas? We're going to use a very, very small quantity of lithium. That's one of the real benefits of looking at things like fusion energy. You are getting orders of magnitude more energy out of tiny bits of mass. So we don't have to worry about that quite as much.
Additional questions? All right, so let's move on. I want to focus on something that you mentioned, which is human health, and I'm going to move this on over to Sandeep. It seemed earlier when you were mentioning about kind of the aha moment and your answer to Matt here, that the data seems really valuable, and there are people who wanted to collaborate with you as an academic on your data. And now one of the asks that you had was that you are raising money, $500K for 18 months. Open, there's rounds open now for a limited time. And for an emphasis in collaborating on the data. What does that mean?
So at this point of time, we have trained our models and developed our algorithms based upon locally available data from local clinics in and around Milwaukee. But what we personally feel is that's not enough. That doesn't make our model really well-performing model if you are using it in somewhere in Asia, somewhere in Africa, so on and so forth. So we need to have a much more diversity in the context of data, the quality in the context of data. So that we don't have an easy access to it. Most of the time they are with huge electronic health record databases. So they don't give it us for free, right? We inquired multiple times with multiple large data set holders who basically sit on these data sets, but they don't do anything. So we have inquired multiple times to gain access to it, but we were not successful. But we will be successful if we have some money to provide them so that they share that as an economical exchange. So to make our models much more robust, make our model much more high performing one, we need to retrain that particular model. So we need to collaborate with individuals who definitely sit on the data sets.
And in the data sets that you currently have right now, without the increased diversity of the data, where can you immediately apply it right now?
So for example, our data set is all based upon Milwaukee patient population. So if you ask me which is the best location to pilot it, it obviously will be somewhere in and around where we sit.
If y'all have a non-healing healing wound, make sure it's happening in Milwaukee. That's the answer here. All right, so we're nearing the end here, and so I want to end it on a kind of a speculative, impact-driven question. So this question will go to every single person in the panel. What does successful commercialization of your technology mean in terms of impact for Wisconsin? And let's start with Adira.
Sure. Yeah. Wisconsin has a lot of bridges, has a lot of dams as well. I think this technology has a lot of potential to, as we talked about, there's a lot of human and cost associated with crumbling infrastructure. And if you think about how Wisconsin is kind of situated and how important our roadways are to accessing our more rural areas, or even connecting the different 11 universities with Milwaukee and Madison, I drive on those roads very, very often. That's what WISES does. We're on the road. I think personally it's going to affect me in having better bridges and roads. But I think from a more global perspective, being a leader in providing better technology for assessing infrastructures will be really important. And as I mentioned, this is a technology from Platteville. This is an area of expertise that Platteville has. And as a university in a rural setting, I think trying to elevate that and trying to bring that into the limelight of here's some really incredible technologies that are coming out of Wisconsin, I think just globally has a big impact for the state. But specifically with this technology, again, with the infrastructure bill and all of the spending that's happening with it, I think it would be great for Wisconsin to take leadership of that and to be a significant player and impact how infrastructure works in the rest of the country.
Great, thank you. Kieran?
Oh, I've got such a great vision for what this will do for Wisconsin. So we're sitting here in Milwaukee today, formerly known as the tool shop to the world. And I think, look, if we're honest with each other, that title probably rests now somewhere in Shenzhen or somewhere like that. But there's still all of this latent know-how in manufacturing. There's a workforce. We've got stellar research institutes and educational facilities. But it's gone through decades of deindustrialization. And like many other cities in the Rust Belt of the USA. So what I really would like to see is let's scrape off that rust and reinvigorate Milwaukee as the center of what we would see as the fusion triangle, right? So Green Bay, to Milwaukee, back into Madison, and hey, we'll take in a bit of Illinois down to Chicago as well. But that's really the fusion triangle. So in 20 years, when Samsung are building a fusion power plant in Korea somewhere, they're going to be sourcing their concrete and their structural steel over there. But when they want to get the precision manufactured components, the high value stuff, they're going to be calling a number here in Wisconsin or emailing someone sitting in Milwaukee or Green Bay or someone. And I think when we look at what Detroit was to the automotive industry in the middle of the 20th century, what Houston is to the oil and gas industry globally today, that's what I would like to see here in Wisconsin, is it being the global hub for the fusion industry. And when you're looking to get your reactors manufactured, your control systems, the robots you need to go in and do inspections, maybe even your structural integrity after an earthquake, all of that stuff is coming from this part of the world. So that's what I see, successful deployment of fusion.
Great. Thank goodness earthquakes don't really happen here, but we get a whole lot of salt, and salt is scary. Sandeep?
Yeah, so chronic non-healing wounds are a significant public health problem globally, and that is true with Wisconsin as well. We have close to 9% of the people diagnosed with diabetes will, at some point of time, if they are not managing it properly, will have chronic non-healing wounds, so on and so forth. And almost like 5% of the people with chronic non-healing wounds in diabetic foot ulcers ends up getting amputated. So it is a huge public health problem. And one problem with having chronic non-healing wounds is that you need to have repeated visit to a facility where you can take care of the wounds, right? You need to have a specialty wound care physician looking at your wound and either changing the dressing, debriding it, and doing all the interventions in a very, probably multiple times a week even. You need to have access to it. So think about a farmer who lives like 70 miles from Milwaukee, somewhere north or somewhere very rural, right? So they don't have easy access to the care. That is a huge problem. So one of our components of the digital health platform is to have a self-management tool in the hands of the patients as well. So patients will regularly monitor their wounds at home, or the caregivers can, or for example, a daughter or somebody who is caregiving them at home can take pictures of the wound, and our algorithms will basically inform them that you are either in the green zone, yellow zone, or red zone. Green zone means whatever you are doing it, continue doing it, because we can see that it is in the trajectory of healing. Orange, you can manage it, yellow, you can still manage it at home, but be careful. Apart from doing what you are doing, add C to it. So if you are doing A and B, please do C along with that. If you are red, you can't manage it at home. Don't play around it at home because it becomes much more a complex issue. So you need to have immediate access to the care. At that point of time, our platform will directly communicate with the provider as well to inform that this particular patient is in the red zone. Either you have to communicate or the patient has to communicate with the provider to get the next step in place to basically get that managed properly. So we provide, at some point of time, with our platform, we will be having significant public health value in the context of our state as well.
Great. On the drive on the way from Madison to Milwaukee, we passed by Aurora, and it was an unusually large hospital in the middle of an area that I don't typically think has a whole lot of people. But I imagine that there are parts of the state there where there aren't a whole lot of access to that type of facility. So having something like that triages you and tells you whether it's worth it to drive on our crumbling infrastructure to get to a hospital seems valuable. Randy?
Yeah, so I'm an associate director of the Stem Cell Regenerative Medicine Center at UW-Madison. And in particular, UW-Madison has a storied history with stem cells. It's one of the reasons I came to UW-Madison, because I was out in California, which is sort of the other, you can go to either California or Boston, or you look up and say, oh, let's go to the middle of the country in Madison. So I came to Madison because of that storied history. And the Stem Cell and Regenerative Medicine Center, the work done by the researchers there, has resulted in numerous technologies, actually, that have been spun out as biotechs. And so I came to be a part of that, and that infrastructure of making these sort of biotech network is really blossoming across Madison, Milwaukee, and other parts of Wisconsin. So I think, just for the state impact, we will contribute in that way. Wisconsin is also an agricultural state. And actually, from talking to Kieran and others, one of the initial applications of our technology is for determining the safety of agrochemical products. So we use lots of products in the crop science world in order to ensure the ability to produce the amount of food that we need. And actually, those products have a storied history in causing neurodevelopmental disorders. And lots of products have been restricted, even today, more recently, EPA-approved products have been restricted because they've been found to be epidemiologically correlated with these incidences of neurological disorders. And so our technology can really make this sort of fundamental industry in Wisconsin even more safe, as well as sort of branch out that findings and that information to the rest of the United States and the rest of the agricultural industry there. Also, Wisconsin, no surprise, is heavily Scandinavian, Nordic sort of descendants, and those particular populations actually have a higher rate of these neurodevelopmental disorders than other populations such as African-based populations, right? And so using our platform, it's really sort of a revolution in medicine now because we have these tools that model early human development. We can use our platform to really understand how we could potentially have prophylactics to neurodevelopmental disorders, and that includes birth defects, early childhood onset disorders, as well as more and more we're finding out that late onset disorders, Huntington's disease, Alzheimer's is another one that's coming up. You can see perturbations to development in the embryo that are later correlated with those disorders. And so potentially the pathways that we need to sort of perturb or prevent need to happen very early on during human development in order to prevent those later incidences. And so my hope is that our technology will have a central role in sort of understanding that and figuring out that science, as well as the compounds that can be used to have that prophylactic effect in order to benefit the populations that are here in Wisconsin as well as around the globe.
Great. For those of you of Nordic descent, make sure to get Randy's information before you leave. Mike.
Yeah. So semiconductors are still an industry that the U.S. is very strong in. A lot of manufacturing is left, but think about seeing Intel inside stickers on your computers. But that's changing. A lot of the advances are moving to Asia now, even in that industry. So being able to take a leap in the ability to make high-performance semiconductors here in the U.S., I think could be really crucial for the whole country and our leadership in this area and preserving this industry here. And it could bring some bits of high-tech industry to Wisconsin.
You know, Wisconsin used to be a center for manufacturing. Between what you and Kieran both said, bringing back and reviving that part of our industry. You know, some people think manufacturing is a step back, and I'm a firm believer that there are enduring industries that will be timeless and needed regardless. And I don't know. Some people believe in the metaverse, and I think Wisconsin, the manufacturing seems more enduring in Wisconsin than the metaverse at the moment.
Including biomanufacturing.
Including biomanufacturing, absolutely. Great. Well, thank you so much. We super, super appreciate the attendees. We super appreciate everyone.
Thanks so much, Nee and Adhira, Kieran, Sandeep, Randy, Mike. We just appreciate your time. I'm going to grab this, and I'm going to just mention to everybody that we really want to thank you for joining us at SummerFest Tech here today. If you've got questions about any of these technologies, I'd encourage you to be in touch with any of these folks. We'll be staying after and entertaining those questions. My colleague, Leslie Mark, is also happy to take questions either today or after the fact. Also want to remind you that SummerFest Tech wants me to remind you that your badge will get you into all kinds of other events later today and tomorrow. More programming at the St. Kate Hotel just across the street. At 4 p.m. there's an ethical machine learning keynote that it will start, and a happy hour mixer that starts at 5. I saw that going on yesterday. That looks like a lot of fun. Your badge is also going to provide you with access to the pitch competition tomorrow morning at 8 at the Marne Art and Culture Hub. It's a networking event that will also take place between 12 and 4 at the SummerFest grounds. So please, to see the remaining event schedule, take a look at summerfest.com/tech. And we want to thank everybody for joining us today on Wisconsin.